Online. Next presenter, Michael Pham, a preliminary implementation of F framework for managing machine learning applications. Take it away, Michael.
All right. Hello, everyone. Let me just fire up my screen share. Okay. So hello, everyone. My name is Michael Pham. I am calling in today from Cal Poly Pomona, just about 45 minutes outside of Los Angeles. I'm here to speak, as the title implies, about a preliminary implementation of using the F prime software framework from JPL to manage machine learning applications. So I'm going to go ahead and I'm going to start with some sort of like groundwork. So our research organization, Bronco Space, we actually started as a undergraduate student organization, and now we're kind of transitioning into being a more formal research lab. What's interesting about Cal Poly Pomona is that we are a primarily undergraduate university, and so we don't award a PhD in any field other than education, and our master's program is rather limited. And so we have a really kind of fascinating cohort of people who come through here and do research, but we've managed to somehow carve out a niche for ourselves doing relatively rapid development. And our average right now is going from TRL 3 to TRL 6 on new technologies in about 10 months. What our lab really focuses on is kind of, starting at around like TRL 3, right? Like taking concepts in on the laboratory side, doing R&D in simulated environments, and then doing suborbital testing. We've done extensive suborbital testing with offices like the NASA Flight Opportunities Office in order to get to that TRL 6. And then we take the technologies to orbit using CubeSats. And so that would be your TRL 7 or beyond. Of particular note is that in the last 2 years, we've launched 4 CubeSats, all of them unique, doing different technology demonstrations. And so that's a pretty fast clip for any organization, but especially a relatively small state university. And currently, what our funded efforts are focused on is this last line here, trying to apply machine learning algorithms to space technologies. So I also want to give one more slide sort of on groundwork where very open source in the lab. We are huge proponents of the open source flight software community. And so I always like to kind of highlight what I see, at least in the CubeSat space, as the 3 primary open source platforms. You have like the ORSAC platform out of Portland State University. They run on GBOS, and they have a really fascinating sort of a app structure. They actually call their framework, I don't, it's like OLAF. They call it OLAF, the ORSAT the ORSAC Linux framework for applications, and they have a really fascinating way of how they implement their flight software. On the right, you also have like the work done at the Hawaii Spaceflight Lab. They have a software product called Cosmos, the comprehensive open software for I don't remember the acronym on top of my head. I really should have notes for this, but they have the Cosmos, but actually they're transitioning their CubeSat work over to F prime framework now, which is pretty interesting. And we're kind of here in the middle path where we derived a lot of our flight software pedigree from the PyCube platform. If you all are not familiar with the PyCube platform, it's introduced a number of years ago by the Robotic Exploration Lab at Stanford. It's pretty fascinating because as opposed to being run on, say, C or C++, like most flight software is, it runs on CircuitPython, which is a fork of MicroPython by the Adafruit Industries group. And it's essentially a Python wrapper for C syntax. And there's like a MicroPython virtual machine that gets deployed to your embedded device that interprets the code in real time. And it's pretty interesting. We've flown it on multiple CubeSats now, and recently out of Ames, the Small Spacecraft Technology Group, flew it for both the VREX and Pi-4 missions. So that kind of brings us to scales, which is sort of the focus of what we're going to be discussing today. Scales is what we call the spacecraft compartmentalized autonomous learning and edge computing system. This project was selected and funded through the University Small Site Technology Partnerships Program last year, and this summer is kind of when we're going to be really cracking into it in earnest. But the underlying reason, right, for scales is to try and create an integrated hardware software system that provides a reusable environment for executing and training machine learning algorithms on orbit. And so the image that you see here is sort of like a nascent version of scales. This is way before we got the USTP funding to do this project. And what you see here actually is a NVIDIA Jetson. This is just Nano, kind of attached to the rest of our flight stack on the CubeSat, a little thermal strap going on there. This was BroncoSat. This is actually our first CubeSat we ever flew. And so we've been playing around with the interface between off-the-shelf edge computing solutions like the NVIDIA Jetson. We've actually used pretty much every single board in the Jetson line in the flight project one way or another. Now we're really just trying to figure out, okay, right, we've seen on multiple flight projects now that like there is a lot of value to having those CUDA cores on board, but having to duct tape together a custom solution for each time is kind of a menace, and also very difficult to create sort of a trust environment for deploying that in anything, less risk tolerant than a technology demonstration. So yeah, kind of a slide kind of iterating like on why like we're working on the Scales project. A lot of it from our perspective comes down to small satellites, specifically CubeSats, trying to have them accomplish more. And the major sort of like benchmark that we're taking a look at is trying to get past the high bandwidth downlink limitation. What you see is that in imaging spacecraft, imaging CubeSats like the one in the picture to the left here, something like this, might be able to generate gigabytes or even terabytes of data throughout its lifetime. But on a good day, we might only see something in the range of like 5 megabits per second down from an S-band radio. And that's presuming that you have the ground station coverage to actually bring things down. And so if we want these small spacecraft, is CubeSat specifically to be more useful and provide more utility for the space community, we need to start putting a lot more autonomy on board. And so where we're coming in with the Scales project is we're trying to sort of marry like off-the-shelf edge computing solutions like the NVIDIA Jetson or Google Coral or something comparable with the F-Prime software framework from JPL. And so this is our funded collaboration that we have. And the idea here is that using the F-Prime framework, we can create a reusable environment around a set of community-developed hardware that can be deployed on multiple small spacecraft with minimal engineering overhead. So some of the pedigree, right, for what we're using to go into this project, these are some of the technologies that we've developed in our lab. On the left panel here, you have Bronco Ember and a little video playing that actually is showing footage from one of the Bronco Ember flights. Bronco Ember is an instrument we developed for autonomous wildfire detection. You see here actually detecting a huge amount of false positives. What you just saw is a lake and some cars going down the highway, not necessarily wildfires. But the onboard computer vision algorithm simply didn't have enough training data to train a good algorithm that's able to reject those false positives. When we were doing Bronco Ember initially, we struggled to assemble a usable data set of wildfire imagery, either aerial or from low Earth orbit. And so a big part of where we're trying to go with scales now is to give the on-orbit asset the ability to use its own data collected in situ to partially retrain or entirely train a computer vision algorithm to detect whatever you might want to detect. In the middle pane here, this is Moonfall, Moon Fast and Accurate LiDAR Localization, not the terrible science fiction movie from a couple years ago. This is an instrument we're developing for autonomous lunar landing. And so the idea is that this would be a sort of feedback system to a lunar lander, generating a 3D terrain map that is able to, you know, give a robotic lander coming in to land on the moon some form of hazard avoidance. We're also, pretty invested in looking at autonomous satellites. One of the concepts we've been shopping around for a couple years is one we call Cadence, CubeSat autonomous detection and networked collaboration explorers. The idea is that you have two spacecraft sort of based off of the Bronco Ember technology here, where one spacecraft has a wide field instrument that's able to scan and pan, or pan and scan for possible wildfires, and a follow-up instrument does sort of a validation observation. And that kind of collaborative autonomy is something that is possible right now, but generally would require a human in the loop. And as some of the previous talks have established, having to have a human observer in the loop really slows down any kind of observation. And that, really makes a big difference either when you're trying to do something, rather time critical, right? Like wildfire detection, or, say you're in deep space and you have the light speed delay to contend with. So kind of just diving into Bronco Ember a little more. It's a 2 degree of freedom gimbal instrument. And so, for our test flights, we flew on a how-to balloon platform. But you could definitely see something similar being put on a hosted orbital payload system as well. So it's able to yaw and pitch. And you might remember from the video that was playing on the last slide, kind of there's a star search pattern. And the idea is that it can go in and do these sort of autonomous detection tasks. The autonomous detection can serve one of two purposes. One is, we can use the detection sort of as a autonomous notification system. What we've seen on our test flights is, if you needed to downlink, like say for, a human to go in and tag that data and say, hey, this is a wildfire. Just the downlink alone would take a couple minutes. And we had the benefit of being on a how-to balloon, which doesn't move very fast from a asset in low Earth orbit, especially if you're a small sat and you don't have access to TDRS, downlinking images in near real time for human tagging is just not really a feasible thing to do from an operational perspective. And so having the computer vision on board to try and do that detection and then just downlink a notification packet is something that we're really trying to get to. Another layer of this, right, is that we can have the instrument do autonomous track as well. And so, like say you wanted to collect data on a nascent wildfire for a couple seconds or minutes, however long you have in your pass. We would want to be able to take the detection that is happening on the computer vision side and then feed that back into a control system for the instrument. So the instrument or the spacecraft, if it's moving the whole spacecraft, can stay on track. And a key thing here is that when we're managing, say, like a high altitude balloon asset with a pretty solid two-way data link, we can just keep an operator at the controls. So if the algorithm goes crazy and we start going off track or something, and we're going beyond the acceptable limits of motion for the instrument, someone can be there to hit the big red button to stop it. But that isn't necessarily something that would be available if we were to deploy on an orbital platform. And so what we're really trying to accomplish with scales is to sort of be able to provide a sort of box, like a bounding box of trust, where the system can automatically reject things that are going to cause issues. On the Moonfall side of things, Moonfall has sort of a different use case for what we're trying to do. You can see actually the instrument system rigged up on the formerly manned and now astrobotic lander. And so when it's coming in to do its autonomous hazard avoidance, we're using a machine learning algorithm to inference through all of the LiDAR and visible camera data streams to create the 3D terrain map as quickly as possible. The challenge we have from NASA is to, from 500 meters, generate a terrain map with 5 centimeter accuracy, 200 meters in diameter in 2 seconds. And the 2 seconds is really the difficult part, because even with our relatively well-optimized machine learning model, it takes about half a second to inference through each iteration of this model with all of the data that comes in. And so what we have been trying to do in order to improve the inference time of this model is training it in a simulation environment, specifically the NVIDIA Omniverse. And in a simulation environment like that, we're generating gigabytes of data for every second that the simulation runs. And our entire library of training data is terabytes in size. And so obviously this is all on the ground, right? We have a big NAS to take care of all of that and big compute. But what we're hoping to be able to accomplish with Scales is a system that actually allows this kind of training to happen in space. The sort of like compute and memory restrictions of edge computing hardware probably won't allow for a very large model to be trained. But there is some really fascinating research out of ETH Zurich about just applying a sort of a reinforcement learning algorithm. And so the sort of architecture there is that you do most of the training of the model in a simulation environment on the ground where you have privileged information and as much compute as you like. You send that model up to your asset in the field, and the asset in the field just has a reinforcement learning algorithm that can tune the weights of that model. And the thing is that, again, we're really trying to create a environment where we can create like a box of trust, right? Where you can do this kind of thing where you can deploy a machine learning model and then have another machine learning model in the field come on top of it and then change it in real time with the actual inputs from the field with some level of trust, right? Some level of trust where that there is a bounding box that some other software will take care of and ensure that you're not going to pilot your spacecraft into the moon or topple it over or something. And so this sort of diagram sort of like sums up like what we're focusing on, right? Where the scale system is going to encompass a primary flight processor and the edge computing module. And this is a similar architecture to what we've used on our flight projects in the past, where the flight processor is something more proven, like a AM3385 or something, or 58. And then that is what is actually talking to all the sensors, the spacecraft bus, the comm system. And the idea is that the flight processor can run a trusted framework like F-Prime to keep the whole spacecraft running and maintain good safe modes. And it just passes in and out the needed information into the edge computer for any high performance computing task, right? Like inferencing through a computer vision model or something similar. And you can create sort of a layer of isolation here, right? Where if the edge computer starts going haywire, you can still have a trap door where you can, play a little get out of jail free card. Sort of where we're starting with this, right, is just locking down a really solid implementation of a simplified state machine for like the CubeSat flight software that manages all of the nominal operations of a spacecraft. And We have a number of CubeSats actually that we're kind of using as a baseline for this. And so we're taking a lot of community input on how specifically university CubeSat developers, because that's a space that we really operate in, how they've all implemented their flight software. And we're trying to amalgamate it into a general solution is a bit presumptuous, but at least a solution that is sort of a compromise solution between all of the different methodologies for doing the baseline like CubeSat software, and then really shaking the heck out of it so it becomes a foundational thing that we can move between different spacecraft, and then just layer whatever high performance application on top. And so this is what we're kind of going for. Our baseline is to try and get like dedicated high performance processing on board with scales that's able to go from current to state of the art for image inferencing, which if you use like the Snapdragon that was on the Mars Engineering helicopter, maybe 4 images a second for a YOLO algorithm, to the state of the art for more terrestrial edge computing, which is many orders of magnitude above that. And yeah, sort of this kind of flow here, right, where we have a reusable environment for spinning up those machine learning algorithms and also kind of parsing in all of the data from the spacecraft bus, and then kind of feeds back out, right, to more mission specific things. I think we're coming up on the time, so that's my last slide. And yeah, happy to answer any questions in whatever time remains. Thank you.
Questions from the audience?
We have a question online. Have you seen any uptime variation throughout the Jetson line? And a second part of the question, how often are you getting reset and what orbit are you in?
Just to clarify, the first question is, are we seeing any uptime variation across the Jetson line? Okay.
Correct.
Yeah. In our experience, I think the most reliable Jetson that we've used so far is the Xavier. The Xavier and the Nano seem to be more stable than the more recent ones. I think just because they've been around for longer, and so the jetpack deployment for them is more stable. What we've noticed trying to use, like, say, like the ORIN, for example, is that we do have a lot of crashing. And so that is part of why, like, we're developing scale so because we want to still be able to access sort of the latest and greatest. But because like the uptime is not as reliable as what's come before, we need sort of a safety net there. For the second question, what kind of orbits we're working with, all of our missions so far have flown to a 500-kilometer sun synchronous on the SpaceX transporter flights. And so one of the concerns there, right, with the polar orbit is also the radiation tolerance of the systems at play. The latest ORIN AGX actually has radiation testing data on it from NVIDIA, which is pretty interesting. The industrial version does. We're going to be collecting our own radiation testing data as a part of the Scales project. And so if you keep up with us, maybe next year we'll have like a repository or something of that data that we can share with folks.
Follow-on question. What Jetson are you using? NX, AGX?
We're primarily
TX2.
using, yeah. So we haven't actually used the TX2. I know the TX2, I believe, has flight heritage, and I think there is radiation test data on the TX2 available on the Goddard Space Flight database. But yeah, we primarily be using the NX form factors. On Moonfall, because we are not constrained to the CubeSat form factor on that, we are using the ORIN AGX, but yeah, we're probably going to keep deploying NX size modules just for the form factor.
Question we have: are you planning on open sourcing this more general flight software core you're working towards?
Yes, yeah. The plan is to open source as much as possible. We don't have a repo set up right now, or the link would be down here. But yeah, the plan is to open source as much of the project as we can.
That's it for questions. Thank you, Michael.
All right. Thank you.